Okay, in this video we're going to be getting into the van der Waals equation. This is something that you may have talked about in general chemistry, depending on who your instructor was. We're going to get into hideous detail of this equation. So the van der Waals is an equation of state. Okay, so I'm just going to write equation of state. And it's an equation of state that can be used to describe real gas behavior. And I really like it because it just builds right off of the ideal gas equation. So starting with that, PV equals nRT. And let's rewrite that in our equation of state notation. So P is a function of N, T, and V. So we'll say P equals nRT over V. And one of our postulates on ideal gas behavior, recall, is that the molecules are so negligibly small, their volume may be ignored compared to the volume they occupy. So as it turns out, molecules do have volume. And if we have enough of them, that volume will be significant compared to the volume that they occupy, right? So we can imagine if we've got some balloon filled with a bunch of gases, this is the volume that they're occupying. But now if we were to consider how much volume each of those molecules actually does occupy, then that dead space or that occupied volume is actually slightly less. So adjusting this for this idea here, we're going to say P equals nRT over V minus, and now we've got to subtract this volume that they occupy from the volume of the actual molecules. So we need to know how much we have. That's going to be number of moles. And traditionally, the letter B is used to indicate the volume of the individual molecule. The volume of the, I was about to write, the volume of the volume, it's the volume of the molecule, okay? So as we might imagine, if we're using liters and atmospheres and Kelvin and so on, if this V has units of liters and we know N has units of moles, this B term has to have units of liters per mole so that we can see the mole and mole unit will cancel. Okay. So now recall another one of our postulates is the molecules have no interaction except for brief elastic collisions. Well, as we just talked about with the compression factor, molecules do interact. So let's write that down again. Molecules do interact. And that interaction is based on their intermolecular forces, okay? So it is molecule specific. Just like the volume of the molecules are molecule specific, so too are the intermolecular forces. And generally speaking, because on most conditions in planet Earth and the way that this equation was developed, in this attractive regime, right, or in the low pressure regime or moderate pressure regime, were attractive. So that's going to have the effect of shrinking these molecules, or really, I should say, bringing them a little bit closer together. So that's another thing that we need to subtract from our overall observed pressure. So I'm going to write our new slightly modified version of the ideal gas equation, nRT over V minus NB. And now recall, this whole thing is going to have units of ATM, if, assuming we use the ideal gas constant with units of ATM. So now what we need to do is subtract the pressure that is changed from the intermolecular forces, okay? And that's going to go with the following. That's going to be A times the quantity N squared over V squared. Because as it turns out, that amount of pressure reduction is dependent on the amount, and it is dependent on the volume. Okay. So as we might imagine now, this A term is going to have units of ATM, but it's also going to have units of liters and moles so that those units cancel. So this will have units of ATM on the top times liter squared divided by mole squared. And each molecule will have a specific A term. Okay? So we could also rewrite this van der Waals equation in this reduced space where we take advantage of Vm. So recall the quantity Vm is V divided by M, our molar quantity. And so I can also write the van der Waals equation as the following: RT over Vm minus B minus A divided by Vm squared, where now that number of moles has just been absorbed into that Vm quantity. So either version of this equation works. And I think the one that has slightly less variables is just a little bit easier to use. So if we look at now what the effect of this is, okay? So taking what might be now the observed pressure and adding back to it, so I'm doing the algebra, right? So this was minus that quantity. So now if I add that quantity over to the other side, we can tease out the effect of just this A term, depending on what the gas is. So as you can see here, that A term, if we scan through, and notice when we have a very small A, it doesn't affect the pressure very much. And my sig figs went missing, so if I recall, there was supposed to be 3 decimal places there. And so you can see with neon to 3 decimal places, we don't see much of a change. But now when we get into argon, which has a significantly larger A term than does neon or helium, we actually observe a significant amount of pressure reduction due to the attraction of those molecules, right? So the molecules are attracting to each other. That's bringing them away from the walls. So if we think about this, right, pressure is a result of collision with the, container walls. So if these molecules are being attracted into each other, they're going to have the effect of reducing the pressure. And so it's pretty cool. I put this in order of the noble gases on the periodic table, right, going down the noble gas row. And you can see what's really happening is we're getting stronger and stronger intermolecular forces as we go from helium to xenon, right, London dispersion forces. And as you can see, there's a noticeable effect on what the observed pressure might be. So now looking at the commonly occurring diatoms, H2N2O2, and I could have gone through all the halogens, but I just picked one. We get the same effect. There's increasing intermolecular forces, so the A term is getting bigger, and thus the pressure reduction is even more noticeable. And of course, if we look at a series of covalent molecules, carbon dioxide, methane, ammonia, water, we can see all of those have very strong intermolecular forces, notably ammonia and water through hydrogen bonding. Those have large A constants, and thus there are significant reductions in the observed pressure due to their attraction. Okay. So we can also tease out what this B term is doing right here from the size of the molecules themselves. And what you can see here is that B is generally a good indicator of how big the molecule is. Interestingly, you would expect neon to have a bigger B term than helium, but remember, chemistry is the science of exceptions. All kinds of interesting exceptions occur. And so with this calculation, the way that I've set this up is if we removed the volume that the molecules themselves occupy, what would be the expanded volume? What volume would we need to fill in their place? So you can see with helium, the ideal volume at STP, right? Remember, this is STP, is 22.42. Well, if we compensated that, it really wouldn't be much different, 22.44, okay? And actually, as you scan down through all of these, you can see because these are all relatively small molecules that I'm picking, probably xenon and Cl2 being the biggest due to their large electron clouds, those still are somewhat significant in the volume change, but not nearly as much as in the attraction change. Okay? So, but of course, we have to consider both of these effects together, right? If I go back to the van der Waal, both the volume of the molecules and the attraction is considered when calculating their real behaviors. So there is competition between those two effects, competition between them actually having non-negligible volume and competition between them being attracted to each other or even them being repulsed by each other. And so to tease out those details even further, we're going to have to look at another equation of state to describe real gas behavior. And we'll do that in the next video, folks. I'll see you then.